So in this video for test review number 2, I want to do the chemical reactions. So one thing to know is how to do these combustion reactions. Hexyne. Okay, so, or hexene. Hexyne. That's a triple bond. Now, the specific structural formula is not needed here. Let's do it a little bit different way. What we learned is that the different functional groups have different ratios between carbon and hydrogen. So a fully saturated hydrocarbon, an alkane, has this formula. Every time you put a multiple bond in, going from a pi bond, you reduce the number of hydrogens by 2. So here has 2 pi bonds, so this is reduced by 4, and the way this formula shows up is like that, where N represents the number of carbons. Well, N is equal to 6 because of hex here. And so the formula that we're using, C6, and then this is H10. Now in a combustion reaction, you should know that the other reactant is oxygen, and then these two react together to form carbon dioxide plus water. And our job now is to go in and balance this reaction. In your typical approach, carbon and hydrogen are done first, oxygen last. Over here I have 6 carbons, I have 10 hydrogens, and I have 2 oxygens. First 2 steps are pretty quick. I need to multiply the CO2 by 6, right? 1 times 6, right? This is basically a multiplier. To go from 2 to 10, I'm going to multiply this by 5, right? 2 times 5, that's 10. And then something that's happened here is that now the oxygen count is totally different than what we started. That's fine, that's normal. 2 times 6, that's 12 oxygens plus 5 more. So I have 17 oxygens total on this side. Now for these combustion reactions of hydrocarbons, the pattern that you see is that half of the combustion reactions, you make it to this step and you have an odd number of oxygens. And then the other half of combustion reactions, you have an even number of oxygens. That's the distinction, okay, as you work these problems. And I've worked a lot of them. That's the pattern that I've seen. So for the odd ones, I want to introduce a technique. You may have seen it before, kind of in the same logic as what I did here, right? These molar coefficients are multipliers. So imagine this formula. 2 times what number can equal 17? It's not a whole number, okay, because that's an odd number. But there is a fraction that you can use here. 17 halves. 2 times 17 halves. 2 cancel out and you get your 17. Let's do that. So technically one can say that this reaction is balanced. 6, 10, 17, 6, 10, 17. It's balanced, but it's not complete. It's not finished. I need to get rid of the fraction, and the way I do that is I multiply 2 by I multiply the entire expression by 2. 2 times 1, 2, 2 times 17, 2 times 17 halves, I just get rid of the 2, 17. So I clean up the fraction, which is my ultimate goal. And then 2 times 6 is 12, 2 times 5 is 10. Little technique of using a fraction in front of a diatomic element, you see this repeatedly in balancing reactions, not just with combustion reactions. Very common with the diatomics. The other reactions are here. So this is a type of addition reaction, and specifically it's hydration. What do you do when you hydrate something? You add water to it. Now in this class we don't get into mechanisms and things like that. Instead we're just recognizing basic patterns. When water in the presence of an acid reacts with a double bond, what happens is that one side of the double bond gets an OH and the other side gets a hydrogen, H2O. I mean, that thing kind of gets split up. Again, that's not the mechanism, but it certainly illustrates how this thing is going to react. And so I go from cyclopentene to cyclopentanol. And no, it doesn't matter how I've rotated or drawn this. I mean, I have a five carbons in a ring structure, and then on one position you have an OH, one position of OH. So I didn't have to stick it right there. I just put it there just because it would look awkward here. Now typically when one sees this particular reagent, that is a hydrogenation reaction if it's an alkene. And in some ways, it's still a hydrogenation reaction. We don't use the language here, at least for our textbook. If the aldehyde is reacting under these conditions, this is a reduction reaction. And by the way, hydrogenation reaction is also a reduction reaction. I think I have an example of that. Yeah, right here. That's a hydrogenation reaction as well. Actually, let's just do this one real quick. Trans 2 pentane, cis-trans really doesn't matter here. I'll go ahead and draw it out. 1, 2, 3, 4, 5, double bond at the number 2 position. Only thing that's going to happen in this hydrogenation reaction, which again is a reduction reaction, the hydrogens are going to add across the double bond there. And you go from an alkene to an alkane. 1, 2, 3, 4, 5. So it's just pentane now. Now, same reagents, different double bond, you still just add hydrogens across the double bond. And when you do that, you get a primary alcohol here. I'll stick with the condensed structural formula. And notice the other, the fluorines here are not affected. Other carbons are not affected. It's just a double bond. And let me just keep it at the same kind of structure like this. So hydrogen of that, what originally was an aldehyde, there's a hydrogen I'm adding, and then let's just convert this to an OH group. So again, the pi bond, the double bond was broken, only a single bond now here. And then those hydrogens that are added would be that guy and that guy. Bromine, molecular bromine is very reactive. This case is another addition reaction, chapter 11. And we call this a halogenation reaction. Now, actually, since it's bromine doing the reaction, you can also call it bromination. If it was chlorine sitting there, it's chlorination. Right? Repeatedly, with these addition reactions, what happens? Well, the double bond gets attacked. In this case, just 2 bromines are attached to these 2 carbons here. So I got 4 carbons in a row. One, and I'll stick with hydrogens that I see. And I have a methyl group right here. And then in orange, I'll bring my bromines at these 2 positions. That's enough. Double bond gets broken, goes to single bond, and then new atoms are added to the double bond. This is another hydration reaction. Now, this one is a little bit different. I mean, it's the same reaction, okay, meaning OH is going to be added to one, hydrogen is going to be added to the other. But notice here, since I have something bonded to this ring structure, specifically at the double bond, I'm actually going to get 2 different types of alcohols here. So in orange, if I draw it this way, OH at this position, I get, and I will try to keep the structure kind of in the same orientation, I get that alcohol. If I instead add the OH there and the hydrogen there, then now I'm going to get, well, basically a tertiary alcohol. So you actually get a product mixture when you do this reaction. And sometimes that happens. Now for our class, we're not worried about what the major product is. We just want to recognize that both of these products can form. Now the opposite of hydration is dehydration. That's acid and heat reacting with an alcohol. So again, we don't focus in on the mechanism here. Proton plus OH is forming water. There's more to it than that if you really look at the guts of the reaction, but that's good enough for us. So it drives off this hydroxy group from the alcohol. In its place, it's going to leave a double bond involving, well, the carbon where the alcohol was, and then one of the adjacent carbons. So it's going to be 1, 2, 3, 4, 5. So it's a 5-carbon chain. And it doesn't matter, cis, trans. Trans is going to be the one that actually forms here. Higher percentage. Again, we're not worried about the percentages. And then what I say is, well, in this, if I'm numbering it in terms of, 1, 2, it's the second carbon over there. And then finally for this one, this is an oxidation reaction. For oxidation reactions, this is a secondary alcohol. Actually, let's talk about that just a little bit. So for a secondary alcohol, how do we identify it? Well, we kind of box in the carbon that's bonded to the alcohol, and there's 1, 2 carbons attached to it. So this is a secondary alcohol. And when secondary alcohols undergo oxidation, they form ketones. So what is a ketone? Well, a ketone is a carbonyl group. Where does a carbonyl group form? It forms where the carbon oxygen is there. Okay, so let's put that in. And then notice to, make it to where carbon has that classic 4 bonds around it, I have to get rid of that hydrogen sitting in there. In terms of reagents, we really didn't focus in on the reagents associated with oxidation. I will say, chromium compounds are really common, but for our test, it'll just be the oxygen atom in brackets to indicate oxidation. And there we go.